Hey Chem Kids, Campbell here. In our third video on stoichiometry, we're going to talk about mass to volume and volume to volume problems. But before we do that, let's do a little review of back in the mole unit. So if you remember back in the mole unit, we converted between moles and liters. And we talked about this thing called STP, standard temperature and pressure. And under those conditions, 1 mole of gas was 22.4 liters. So that was our conversion factor. If we had moles, we multiplied by 22.4 to get to liters. Or if we had liters, we divided by 22.4. Well, in stoichiometry, in a mass to volume problem, we're going to start with mass, so grams of some substance, substance A. We're going to go through our heart so that we can convert from substance A to substance B. And then we're going to end up by multiplying by our 22.4 to get to our substance B. So if we go to our steps, first step, right, is we have to balance the equation. Now I say if needed because in this video I've already balanced them for you, so less talking and work. But if you don't have a balanced equation, remember you have to balance it because that's what goes in our heart. Then always write down what you have and identify what you need to find, right? There's always so many words in there. Look for the number and the unit of what it is. Write that down and then identify what it is that you're going to find, because remember that's going to go in your heart. The first step, because we're going to be in mass, so we'll be here in this diagram, right? We're going to divide by our molar mass. So from the periodic table to get us to moles, right? First step when we have mass is divide by molar mass to get to moles. Once we go through that step, right, then we're at the heart of our stoichiometry problem where we multiply by our mole ratio. Remember, the mole ratio is the numbers that come from that balanced chemical equation, and it's always finding what we're trying to find in this problem, our question mark, over what we've been given. And then our last step is great because all we got to do is multiply by 22.4. We don't have to go to the periodic table. It's beautiful. We just multiply by 22.4 and boom, we are done and we're in liters. So let's try this. So here is a reaction of, this is called sodium azide. It's actually in your airbag, and that's what causes your airbag to inflate really quickly because it produces nitrogen gas. So it says if an airbag contains 125 grams of sodium azide, what volume of nitrogen gas is produced at STP? Again, don't worry about the STP. We didn't worry about it much in the mole unit. So kind of ignore that. But again, look at our number and our unit and what it is. So this is what we're starting with. So I'm going to write this down right here so I don't forget about it. We have 25 grams of this, and it says what volume of nitrogen gas is produced. So what I'm trying to find is nitrogen gas. All right, so first step is balance. Well, that's done. Second step is write down the number and the unit and what it is. So we're starting out with 125 grams of NaN3. Now we have grams, so remember the next step is we have to go to moles, and we do that by dividing by the molar mass. And remember the molar mass comes from our periodic table, so we need our periodic table. So I'm going to make a little molar mass table here. We have Na and we have N, and I always do number of elements, and then the atomic mass from our periodic table. We only have one sodium, and on the periodic table, sodium is like 22.99, so I'm just going to round that up to 23. Nitrogen, there are 3 nitrogens in my formula, and on the periodic table, nitrogen is 14, so we're going to multiply these numbers by that. So I have 23 grams per mole of sodium, and 3 times 14 is 42. For my nitrogen, and if we add 23 plus 42 together, right, we add these together to get our molar mass, that's 65. All right, so now we know our molar mass of the sodium azide, so we're going to take our 125 grams and we're going to divide by 65 because that's the conversion between grams and moles. All right, so in your calculator, take 125, divide by 65, and you get about 1.92. So I'm just gonna have 2 decimal places here. It's up to you how many decimal places you want to keep. I'll just keep 2. because there are 3 significant figures in this problem, so we'll stick with that. But you know how I feel about significant figures. Na(N3). Okay, so that's what we have. So next step, right, is the heart of all stoichiometry problems is our mole ratio. So on the bottom is our Na(N3). Because that's what we were given. What we're trying to find is we go up and find that question mark, that's N2. So remember, this is a mole ratio, and the numbers that go in it come from this balanced equation. So I find my Na(N3), it's right here. That number is a 2. So that means I have 2 moles of Na(N3). And oops, this is supposed to, yeah, that's my N2. That's a 3. So that means I have 3 moles of N2. So 3 moles of N2 per 2 moles of sodium azide, Na(N3). So that means I'm going to take a 1.92, multiply that by 3, divide that by 2, and if you do that, you're going to get 2.88, and we are now in moles of N2. But we're not done. We don't want moles of N2, right? We want the volume, and the volume is going to be in liters. So we're going to take our 2.88 moles of N2, and we're going to multiply, right? When you have moles, you multiply by 22.4, because that's our conversion between moles and liters. So if we do that in our calculator, we're going to get 64.6 liters of N2. All right, so mass to volume, balance your equation, write down the numbers of grams you've been given, divide by the molar mass of that substance, then do your heart, your mole ratio, and then last step, multiply by 22.4. So let's try one more. All right, here we go. How many liters of hydrogen gas is needed to produce 1,000 grams of water? So step 1, balance your reaction. Oh, done for you. Hey, yay. We want to know how many liters of hydrogen gas. So that's our question mark. There's our hydrogen gas, so there's our question mark. Is needed to produce 1,000 grams of water. So I have 1,000 grams of this. All right, so step one, balance the reaction, done. Step 2, write down the number and the unit and what it is. So we have 1,000 grams of H2O. Now we're in grams, we got to get to moles. So remember, when we have grams and we need to go to moles, we divide by molar mass. So I'm going to make a molar mass table here. I have hydrogen and oxygen, number of elements, atomic mass from the, oops, that's supposed to be a P, periodic table. So we have 2 hydrogens. On the periodic table, hydrogen's like 1.01, but I'm just going to round that to 1 to make, life a little simpler mathematically. So there's 2 grams per mole of hydrogen. There's only 1 oxygen. Oxygen is 16 on the periodic table. So my total molar mass of water is 18. So we're going to take 1,000 grams of water and we're going to divide by the molar mass of 18 grams per mole. So in your calculator, 1,000 divided by 18 should give you 55.6 moles of water. Now, again, keep however many decimal places you want. I kept 1 here. Honestly, there's only 1 sig fig in that number, but I don't want to round that to 60, so we're just going to leave it at 55.6. Or whatever you want to round that to. All right, next thing, we have our heart, right? The heart of every stoichiometry problem is our mole ratio. So on the bottom is what we were given, that's the water. On the top goes what we have our question mark with, which is the H2. So when I look at my reaction, the number in front of the H2O is 2. The number in front of hydrogen is 2. Oh, well, that makes my life easy, right? 2 over 2 is just like 1. If you don't believe me, go ahead. 55.6 times 2 divided by 2, you get 55.6. But now we have moles of H2, what we're trying to find. All right, but we're not done because we don't want moles of H2. We want liters of H2. So we're going to multiply that by 22.4. Because that's our conversion between liters and moles. All right, when we do that, we're going to get a big number. It's 1,244 liters of H2. All right, so there we go, mass to volume. Convert your mass to moles, do your heart, and then convert your moles to liters. All right, let's take a look at one more type of problem. It is called a volume to volume problem. So in a volume problem, we're starting with liters, or if you have milliliters, make sure you convert it to liters. When you have liters, you need to go to moles, right? So when you go to moles, you divide, and so we'll divide by our 22.4. And then we do our heart, right? There's the heart of our stoichiometry problem, to go from moles of what we've been given to moles of what we're trying to find. And then our last step is the step that we were just doing last in our last problems, which is to multiply by 22.4. Now, what's really interesting about that, right? If we divide by 22.4 and then we multiply by 22.4, they kind of cancel each other out. It's really kind of just multiplying by 1. So in fact, we can treat these mole ratios as volume ratios because really they just cancel. So really all you got to do is the heart, just like a mole to mole problem. But you know what? Don't take my word for it. Let me prove it to you. So here is a reaction of ammonia with hydrogen gas, nitrogen with hydrogen gas to produce ammonia. And I want to know what volume of hydrogen gas reacts with nitrogen to produce 6.5 liters of ammonia. So I'm starting with 6.5 liters of ammonia, NH3. I want to find the volume of hydrogen gas. Don't ignore all this blah, 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 blah. So just what are we trying to find and what are we starting with? All right, so step number 1, right? We balance our chemical reaction. It's already balanced. Life is good. Step 2, I guess we should say, is to write down the number and the unit of what we were given. So that's 6.5 liters of NH3. When we have liters, right, we need to divide by 22.4. So no periodic table here. Isn't that nice? Because there are 22.4 liters per mole. So if we take 6.5 and we divide by 22.4, we're going to get 0.29 liters. And sorry, liters. That's not liters. That's moles of NH3. All right, so we check with that step. Next, we go to our heart. So we're going to multiply by our mole ratio. So the NH3 is what we're given. So that goes on the bottom. Our question mark is the H2 that goes on the top. In front of the NH3 is a 2. In front of the H2 is a 3. So we're going to take, I have to write this down here. We're going to take our 0.29, we're going to multiply by 3, and we're going to divide by 2. When we do that, we get 0.44 moles of H2. All right, last step is to multiply by 22.4, just like in our last problems we were doing, because that's our conversion from liters to moles. And if we do that, we're going to get 9.75 liters of H2. Okay, so there we did the whole thing, the divide by 22.4, the heart, the multiply by 22.4. But you know what? This and this just cancel each other out. So let me show you that. Let's do this again, but let's do it this way. Instead of going through the 22.4 process, why don't we just go right to the heart? So again, same exact question. Step 1, balance your reaction, balanced. Step 2, we're starting with the 6.5 liters of ammonia, and we want to find the volume of H2. So we're going to write down our number and our unit and what it is. So we have 6.5 liters of NH3. If we go right to the heart, right, then NH3 goes on the bottom. We're trying to find H2. That's my question mark. That goes on top. All right, so we put the 3 on top and the 2 on the bottom. And so if we do 6.5 times 3 divided by 2, guess what you get? It's 9.75 liters of H2. So if you want to, do the whole process, divide by 22.4, then do the heart, then multiply by 22.4, you go. But all you really got to do is just the heart. So let's do one more. All right, I have 100 liters of hydrogen gas reacted with oxygen gas to produce water. How many liters of oxygen gas are needed? So I have 100 liters of hydrogen gas. So that goes right there. Blah, 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 blah. How many liters of oxygen gas, so that's what I want to know, are needed? All right, so step 1, balance your equation. Check. Step 2, write down the number and the unit and what it is. So we have 100 liters of hydrogen, so that's H2. Remember, volume to volume, we can skip the whole 22.4 thing and go right to the heart. Hydrogen goes on the bottom. We're trying to find oxygen, that goes on top. Oxygen doesn't have a number in front. Remember, that's just 1. The hydrogen has a 2. So we're going to take 100 and multiply by 1, divide by 2. Right? That's like multiplying by half. And we get 50 liters of oxygen gas. See? Volume to volume. That's so easy. So that's it. Mole ratios, the heart of all of our chemistry problems. We have mole to mole. We have mass to mole, or actually mole to mass also. Mass to mass, mass to volume to volume. All of those things, we use our mole ratio because it's the heart of all our stoichiometry problems. We got one more to talk about, it's percent yield. So I'll see you in class.